sure you see all the connections. You see all the connections. Okay? So, why related rates? A university student is concerned that the rate of their increase in financial aid is lagging behind the increasing cost of tuition and fees. A renter is concerned that his rent is increasing faster than his take-home pay. An automobile manufacturer wants to predict how much an expected increase in the car loan interest rates will decrease her rate of sales. Union workers are concerned that the rate of increase in their wages is falling behind the rate of increase in their company's profits. In each of these situations, there are two quantities that are changing with respect to time. So the idea here is we've always been dealing with X or T, or always one letter. Now, how do we deal with two variables? Two variables. So the study of related rates provides a method for determining the precise relationship between the rate of increase or decrease of two quantities. We begin by examining related rates with an example where the two quantities are distances and the two rates are velocities, the rate of change in distance over time. So, example 1. A 26-foot ladder is leaned against the wall. The ladder slips and the top of the ladder begins to slide down the wall. As this happens, the bottom of the ladder slides along the floor away from the wall. So, we have a ladder against the wall. So the ladder is 26 feet. The distance away from the wall we'll call X. And the distance, the height of the ladder along the wall is Y. But this ladder is falling slowly. As it falls, it goes down the wall and it goes away from the wall. Away from the wall on the right. So if the top of the ladder slides down the wall at 2 feet per second, stop there. 2 feet per second is a rate of change. Rate of change is derivative. Are we okay? 2 feet per second, that's rate of change. At what rate is the bottom of the ladder moving away from the wall when the bottom of the ladder is 10 feet away from the wall? So, we're letting X be the distance from the wall to the bottom of the ladder, Y being the distance from the floor to the top of the ladder. As previously noted, since the ladder is sliding down the wall and the bottom is moving away from the wall, both X and Y are functions of time. X of t, t is time, Y of t, t is time. Furthermore, they're related through the Pythagorean theorem. So here's our first equation that I want you to write down. Because we've made a right triangle, we know that x squared plus y squared equals the hypotenuse squared. So here's our first equation. X squared plus y squared equals 26 squared. Every equation, you need to understand where it comes from. Does everyone see how I got x squared plus y squared equals 26 squared? One equation, but here's the problem. How many variables do I have? 2 variables. 2 variables. Okay? Differentiating the Pythagorean theorem implicitly, that's the section we skipped, with respect to time gives us this. So let me show you how we got from one to the other. Okay? So you have the first equation, x squared plus y squared equals 26 squared. Okay? And let's simplify that. What is 26 squared? Don't put that in the calculator. 26 squared. What is it? 676. Are we okay? Now, this just tells me the distance from the wall, the distance up the wall equals 676. I'm trying to find how things change. Rate of change. So anytime I say rate of change, that means what? Derivative. Are we okay? So let's take the derivative. What's the derivative of x squared? 2x. Does everybody see how I got 2x? Now what we did was the derivative of x with respect to time. This is what we skipped in section 3.5. I took the derivative of x, dx, with respect to time. Okay? Now I'm going to do the same thing for y. Plus, what's the derivative of y squared? But this time, it's the derivative of y with respect to t. And what's the derivative of 676? 0. Stop there. Does everyone see how I got my second equation? Does everyone see how I got my second equation? That's the trick of this lesson, is that everything has to make sense. Everything has to make sense. Any questions so far? Okay. Back to the notes. So dx over dt and dy over dt are related through the derivative result. This result confirms that this is a related rates problem. In this example, we're trying to find dx over dt when x is 10 feet. So we know that x is 10 feet. So we know that x is 10 feet. We're looking for dx over dt. That's what we're looking for. We know that x is 10 feet. That's given to us. And then they tell us dy over dt. This is new, so let's talk about what that is. dy over dt is how y is changing. How y is changing. They told us that y, the distance up the wall, is falling. So do you think falling would be negative or positive? If it's falling. You think falling would be negative or positive? Negative. And how is it falling? It's falling 2 feet per second. So all of this is given to us. All of this is given to us. We're trying to find out how is the x changing. What's the rate of x? Dx over dt. We know that x is 10, and we know that y is falling. The derivative is the rate of change, falling 2 feet per second. Since we know all that, we also know, well, and actually we can go back and plug in. We can find y first. So first, let's find y. So I'm going to take this equation, x squared plus y squared equals 676. How can I find y? I know what x is. X is 10. So I can say 100 plus y squared equals 676. Subtract 100, subtract 100. Y squared equals 576. Now, do I want y squared or do I want y? Y. So how do I get rid of squared? Square root, square root. Therefore, y gives you square root of 576 is 24. Now, technically, you get negative and positive 24, but remember, y is a distance, so it has to be positive. Now, why did I need y? Well, bottom line, I'm looking for dx over dt. Do I have x? Yep. Did I have y? No. So I have to plug into the first equation to find that. Do I have dy over dt? Yep. So now I have all the pieces. Now I have all the pieces I can now solve. So I'll try to put this all on one page if I can. So now we're going to use this equation, 2x times dx over dt plus 2y times dy over dt equals 0. And we're going to plug in everything we know. So 2 times what's x? 10. I don't know dx over dt, which is what I'm trying to find. I know y is now 24. I know dy over dt is negative 2. And then what's your job at this point? Bless you. We need to solve for dx over dt. We need to solve for dx over dt. So let me give you a minute to write all that down. And if you're trying to figure out what are we doing here, what we're doing is we have two equations. We're trying to solve for something. We find everything we can find, and then we can plug in and solve for what we want. Then we can plug in and solve for what we want. So let's do a little algebra. What's 2 times 10? 20. 2 times 24 times negative 2 gives you negative 96. And then how do I solve this? What would be the next step algebraic? What would you do? Add 96, 20 dx over dt equals 96. Then what? Divide by 20, divide by 20. What I've been searching for, dx over dt, which is the rate of change of x, how x is changing, is 4.8 feet per second. 4.8 feet per second. Okay, so stop there, and I'm going to review everything from the top. So the nuts and bolts of this, related rates, is that you have a picture, you take the picture, and we get some equations out of it. So in this case, okay, we looked at our picture and we got the equation x squared plus y squared equals 26 squared. We got that. Because it's talking about how it's changing, rate of change, we took the derivative of that and we got the derivative of x squared is 2x. But because we're taking the derivative of two variables, this is called implicit differentiation. We took the derivative of x, which is 2x, dx over dt, the derivative of x, plus the derivative of y squared is 2y, dy over dt. We took the derivative of y with respect to t, and the derivative of 676 is 0. Then we looked at what we had. We're looking for dx over dt, how x is changing. It was given that x is 10. It was given that dy over dt is negative 2. So looking at this equation, I have x, I'm looking for dx dt, but I don't have y, but I have dy over dt. So looking at what I had, I could find y by going to my original equation, plugging in x, finding y. Now I have all the pieces to plug in the equation, 2x times dx over dt plus 2y times dy over dt equals 0. I plug in everything except for dx over dt, which is what I want, and then I can solve for dx over dt. And more importantly, what does all this mean? It means that we found that x is changing How is it moving? It's moving 4.8 feet per second. And the reason why it's positive is it's moving away. It's not going towards, it's moving away. 4.8 feet per second. Okay? What you should take away from this is we're using derivatives, y, rate of change, how something changes. This is another application. All right? So, some advice. Sketch a figure. It helps. Make sure you identify what all the variables are. Express all the rates and what you need to find. Find an equation connecting the two. Implicitly differentiate the equation. Define the derivatives. You may have to use different rules. And then solve the derivative to give you the unknown rate. Okay? So here's another one. Again, breathe, relax. We'll do it all together. Suppose at a moment a westbound plane traveling 120 knots is 120 nautical miles from an airport. A northbound plane traveling 160 knots passes directly over the airport. So stop for a second. The reason why this is related rates is I have traveling 120 knots. That's a speed. That's a rate of change. 120 nautical miles is distance. 160 knots is the derivative. It's how it's changing. So let's get our equations, and then we can start working. So how fast is the distance between the planes changing 1.5 hours later? Assume the planes continue at the same speed and direction. Okay? So let's draw a little picture. Let's draw a little picture to talk about this problem. Okay? So here's our picture. Make sure we understand the problem. Here we have the airport. And we have one plane going north. And that plane, oh, a really cool plane. Really cool. It's going 160 knots. That's how fast it's going. Another plane is going towards the airport. At 120 knots. That's the speed. And if I connect it like this, we have a right triangle. So it's kind of like the last one so far. Now remember, knots is how fast it's traveling. How fast it's traveling. Now, just like last time, because we have a right triangle, let's call this one W for westbound. Let's call this one N for northbound. And we'll call this one D for distance. So, I can take the westbound squared distance plus the northbound distance squared, and that's going to equal the D squared. So there's my first equation. I'm going to stop. Does everyone see how I got that? And those are all distances. Distances, not rate of change. Those are distances. Now, just like last time, we're going to take the derivative. So if I take the derivative, this will be what? What's the derivative of y squared? Or w squared? 2w, but this will be derivative of w with respect to t. Plus 2n, derivative of n with respect to t, And again, the whole taking the derivative of each letter, that's called implicit differentiation. And what's the derivative of d squared? 2d derivative of d with respect to t. Now there's a lot of letters, but now we can start filling some stuff in. We can start filling some stuff in and figure out what we don't know. Now going back a little bit to what's given, they told us the distances. They told us the distances, okay? They told us a couple things, okay? First of all, they told us that the northbound plane is 80 miles away. They told us that the westbound plane is 60 miles away. So let's stop there a second. I know the northbound. I know the westbound. What do I not know? I know N. I know W. What am I missing? D. So, stopping there for a second, can I solve for D? Can I solve for D if I know N and W? Okay, so W squared plus N squared equals D squared. W is 60, N is 80. Can I solve for D? Yep. So just like last time, we start solving. As I solve, I get D squared equals 10,000, square root, D equals the square root of 10,000, which is 100. Stop there. Any questions? So you're given, you got two equations, you're given some pieces, and you got to start solving for the rest. Now, they did also tell us some more stuff. They told us the speed of N and W. So dN, that's the speed of N, how fast that northbound plane is going, is 160. They told us the speed of the westbound plane, that is negative 120. Now, let me explain why it's negative, because it's going towards, not away. Away is positive, towards is negative. Away is positive, towards is negative. And your job is to find d, derivative of t, here. So, bottom line. There's everything that's given. Here's the equation that we're working with. What you need to do is plug in everything you know and solve for what you don't. Plug in everything you know and solve for what you don't. Okay? That is the bottom line. I know it's getting crazy because we have so many variables, so many things going on. But the bottom line is, we have two equations which we've gotten. We can solve to find out what we know. And then eventually, we're going to have one thing left. In this case, it's derivative of d with respect to time. It's how fast would that plane be going? So we fill in all the stuff we know and then solve for what we don't. We fill in all the stuff we know and now solve for what you don't know. So plug in everything you know. Solve for what you don't know. Plug in everything you know and solve for what you don't know. So you got that last equation, plug in everything you know and solve for what you don't know. I'll give you some time to do that. And then you'll find how the distance between the planes is either increasing or decreasing and at what rate. Okay, so let's make sure we're plugging in correctly. We know W is 60, so 2 times 60. We know dW over dt is negative 120. We know N is 80, so 2 times 80. We know dN over dt is 160. We know d is 100, but the one we got to solve for is dD over dt. So let's make sure we filled everything in correctly. And then now solve. We get so far, cleaning it up, 2 times 60 times negative 120. Negative 14400. 2 times 80 times 160. 25,600. 200 dD over dt. Then negative 14,400 plus 25, 600, 11,200 equals 200 dt over dt. What's the last step? Divide by 200, divide by 200, dt over dt equals 56 pounds. Okay, so what I want you to pull away from this, is that you have a bunch of variables. We understand what each variable means. We plug in what we don't know, we plug in what we know, and we solve for what we don't know. We plug in for what we know, and we solve for what we don't know. Okay? Do one more. And I want to really focus on, once it's all laid out, to solve it up. Once it's all laid out, to solve it up. And really what I want you to get away from this is what everything means, what all the variables are, what we're getting from all this. Okay? So one more. Okay. Example 3. So suppose a point is moving in a circular path centered at the origin and radius 5. The graph has an equation, x squared plus y squared equals 25. That's the equation of the circle. And we have a point on that circle, negative 3, 4. When the point is located at negative 3, 4, its x-coordinate is increasing at a rate of 0.4 units per second. That's the rate, 0.4 units per second. How fast is the y-coordinate changing at the moment? We know how fast the x-coordinate is. Now we're trying to find out how fast the y-coordinate is changing. So let's take this nice and slow. First of all, we're given the equation x squared plus y squared equals 25. That's what you're given. Okay? Let's start with that. They should look very familiar, just like the last two. We want to know how things are changing, rate of change, rate of change. So what do I need to do? Take the derivative. But I have two different variables. When I have different variables, we're going to take the derivative of x squared, which is what? 2x. What did we just do? We did the derivative of x with respect to time. Starting to look familiar, hopefully. That's why we're doing 3 examples. Plus, what's the derivative of y squared? 2y, derivative of y with respect to t. Then, what's the derivative of 25? 0. Stop there. Now, this is what I'm trying to get to. And we're doing 3 examples. Okay? X and y are just a point. X and y are just a point. X, y. X, y. dx over dt is the rate of change of x, how x is changing. dy over dt is how y is changing, derivative, rate of change. Now for this one, it's going to be a little faster because you're given the point negative 3, 4, which means what's x? Negative 3. What's y? And you're also given one more thing. You're given how x is changing. You're given how x is changing. First of all, what's the symbol for how x is changing? dx over dt. And that was given as 0.4. So basically, you have everything except what? dy over dt. Your job is to find how y is changing. So, since you have everything already, you can just plug straight into the equation 2x times dx over dt plus 2y times dy over dt equals 0. Okay? So that's what I want to get to, is what everything means. What everything means. What everything means. What everything means. Give it 1 more minute, plug everything in, and then solve for what you have left. Plug everything in, and then solve what you have left. Okay? So, let's fill in what we know, what we don't know. So as I fill this in, do I know what x is? -3. Do I know what dx over dt is? 0.4. Do I know what y is? Do I know what dy over dt is? Nope. So you plug in everything that you know, you plug in everything that you know, and then your job is to solve for what you don't know. Your job is to solve what you don't know. So 2 times -3 times 0.4 gives you -2.4 plus 8 dy over dt. I would add 2.4, add 2.4, 8 dy over dt equals 2.4. Then what would you do? What would you do? Divide by 8, divide by 8, dy over dt equals 0.3. That would be how y is changing. X per unit per second. Okay? All right, let's stop there.